evening. It gives me immense pleasure in interacting with you all on the occasion of this technical seminar, which is being organized by the Institute of Indian Foundrymen Chennai chapter here at Southern Crown Hall, Hotel GRT Grand Chennai. Before we get started, requesting all participants to please put your phones on silent. To get things started, may I now request Mr. Shaktivel R. T.Nagar, IIF Chennai chapter chairman, to welcome the gathering.
Good evening, everybody. It's being a pleasant evening. We are here to have a program of Mr. Charles Essman. We have been chasing him for maybe 3 years, roughly 3 years, and we got him lucky this time at least. He's been in Chennai. So needless to say about the refractory, so very important for the furnace. Not only that, it's also safety point of view. So today we are going to have a very good discussion on, after a long time, Chennai is having a refractory program. So please enrich yourself on today's knowledge sharing session. Not only this, every week we are doing a program, is online or a physical program. So 1 week, one program. Please join our programs every week to the online program, or else you can subscribe for IIF Chennai at YouTube channel. So you can have all listed, all our programs are listed. You can go through that and get yourself knowledgeable, right? So with this, I invite Mr. Charles to.
Chairman, it gives me immense pleasure in introducing our speaker for the evening, Mr. Charles Essman. He's the International Business Manager Sales at Allied Metal Products USA. With his educational background, he's an industrial engineer from Ohio State University. Mr. Charles Essman is associated with Allied for more than 30 years. Mr. Essman has worked at various key positions in Allied, including production, training, sales, and marketing. He served in more than 40 countries worldwide and extensively traveled to South America, Mexico, Europe, South Korea, Japan, Middle East, Africa, China, and India through these years. Mr. Essman also established and run the Texas manufacturing plant of Allied Metal Products and was general manager of the plant for 5 years. He joined the international sales again in the year 2006 with a focus in India, Middle East, and Brazil. And currently he is very focused on the market of the Indian subcontinent. Chuck, as he's known among his family and friends, is having a very rich knowledge and of all types of metal melting industry, from conventional to most modern methods and practices used worldwide. I'd like to say that Chuck is almost like a half Indian. He's been coming into India for more than 15 years, and he's very familiar with our food and with the people. He loves meeting people and solving their issues, going into customers and taking a lot of seminars. So the stage is yours, Sri Chuck.
When we're in Chennai, that just shows the commitment to the industry and the commitment to your companies. So I really appreciate everybody coming out. It's nice to see so many old friends, and it's good to see some new ones as well. So the only thing I'm going to ask is that maybe you wait until the end of our presentation, take some notes, and we can answer questions at the end, if you don't mind. With that being said, we'll get started so we can have dinner soon, okay? The first thing we were going to talk about today, I think the chairman kind of touched on it today, was safety. And there's a lot of things happening, especially with silica around the world, that's creating a need to change in what people are using. Safety and also some chemical aspects of it also. So we're going to start out with one, which is basically was driven by the need in Europe to get away from boron in the castings. And that boron is being taken from the linings in the form of boron oxide. So we've developed a product that's boron-free, relatively boron-free, and it's showing great promise. Like, it's an experimental product. It's being used in about 4 locations at this moment. This is one in Canada in particular. The XMDV BF1, these are just codes. It'll be a mineral of some type eventually, or Silvive at one time. So the boron-free silica, the problem with boron is that once you get into your metal and it's too high a quantity, it's very hard to machine it. And so you go through more machining tools, you go through more machining time, and it increases the cost and reduces the quality. So this is just kind of an introduction of what this foundry is. It's an automotive foundry. They make various automotive parts, from transmissions all the way to other areas. So in the past, the customer used to have to wash boron coming from the liners by melting 65 ductile iron grade alloy, and after 3 heats, they could switch over to 80 to 100 grade ductile iron. And then one day they stopped selling the 65 grade. So they had no choice but to do wash heats, because their customers, as we're finding in Europe, a lot of the customers are requesting that the boron content come down. So they would have to actually melt 3 heats and just pig it out in order to get to a point where the lining no longer was capable of giving the boron. So this foundry has a 3.5 ton ABP and 2 9-ton ABP furnaces. They used to use, this is probably something that's never been seen in India, but it's used in Canada. It's also used a little bit in Europe. It's called LD, which is low dust silica. And again, that was made back in the early 90s, mid 90s, in order to reduce the amount of dust that people breathe in during an installation. And we have new products for that, which we'll talk about later, okay? So method of charge is with a magnet, and they have different top capping methods, which we'll talk about later too, but it's not really what it's about on this one. So, as you can see, they're filling the walls. Basically the same process. There's nothing different as far as the installation goes. The installation process is exactly the same. Now, what they found, and this has been an issue with this in the early stages, is the customer had started, they centered it exactly the same way that they do in their standard linings, which is about a 18-hour center cycle with solid charge. And the center schedule has been followed as required by them, actually. The first impressions weren't good from this particular customer. In the initial hot face, you can see a little bit of peeling of the liner right down in here. And that peeling was very thin. It was skin, mostly, like a skin peeling. So, but what they did like is that their boron on the first tap was at 0.00036, almost non-existent. And that was well within the specifications of their customer. So, as you can see, first couple of days were not easy. They had hot face issues, which concerned them because it was a new product. We don't blame them whatsoever. After 3 days, they were stabilizing. The wear rate stabilized once we lost the initial peeling of the hot face. And the lining ran quite well after that, actually. It really wasn't an issue. So 70 tons, 300 heats. The only place that we still had an issue was in the bottom. There was some of the bottom that was missing. But not enough to cause any harm or damage or even alarm. So mid-campaign they stopped. The customer decided to push it at 320 tons. They could have gone longer. The lining was still perfectly good. But since it's an experimental material, they wanted to take a look at it just to see. Okay, before we sold the ideal rammer, campaigns for the LD10BO was 650 tons. Now they're using the ideal equipment, and the campaigns go up to 850. They were using a different vibrating method that just wasn't sufficient for their needs, and just by changing the vibration method, they were able to get better lining life. So during the operation, nothing out of the ordinary happened with the boron-free silica, except for the walls being a little brittle. Furnace readings were normal, no visible cracks, and infiltration was visible. So then they took it out and they basically, analyzed every layer as they were taking it out. As you can see, there's still about 100 mm of lining left in this lining. You can see there was quite a bit of loose backup still present in that lining. So that lining could have gone a lot further. But they took it out again just so they could do an analysis, since it was the first time that they used it. So now we went to the second, and they wanted to find a way they could control the center a little bit more without, adding, boron oxide, of course. So Allied has a product, it's here, it's called DV Defender. DV Defender is a paint, and you paint it on your former, and you let it dry overnight, and then you do the installation of your silica just like you would normally. But during the center cycle, this is a very low melt temperature coating that seals the silica, seals the porosity of the silica. So it makes it a little bit easier to center a furnace. And we thought that if we tried this, this may eliminate the peeling that we had, those issues. So it also, instead of boshing every layer in the floor, we only used ideal rammer, but doubled the time of the compaction. After 95 tons or 40 heats, we could see stronger hot face than the first lining had. Boron reading at the first tap was 0.0002. First cool down after 140 tons, 60 heats, there was some brittle material on the floor. And we have, they've sent samples to be analyzed, but again, it was nothing alarming. The lining could run a lot more time. Oops, sorry. Liner walls after a couple of cold starts. After 92 heats, the walls are looking great still. We're still teaching, we're still targeting 850 tons. So after 400 tons, observation is the wear was the same as standard silica, except on the floor. And of course, the boron content is coming way down. Like I said, this is an experiment. We've been working on this product. Some of our competitors have also been working on this product for up to 10 years. Believe it or not, you think just taking boron oxide out and putting another bond in would be easy. Turns out it was not. So this took a very long time to develop. This is probably the third generation of mixes that we've made. And I think that we finally found a winner in this one. So if you have any concerns with boron content in your castings, we have this available if required. So the second lining push out. They stopped after 523 tons, but liner was still good. Again, they wanted to get it out so they could, they had to do maintenance of the furnace, but they also wanted to see it again, to see what it looked like with more heats on it. Step by step by step, they just wanted to be careful. In concordance with usual campaign, there was no difference. They checked their lining every time they take it out. Hard face had an overall thickness of 1 inch. Wall thickness in the midsection was 3 inches. And you can see that we had a very good hot face formation, followed by a very good semi-centered zone. So everything was good. The floor section, again, they did notice a little bit faster wear in the floor. So that's a concern, and that's something that we're working on. But none of the erosion in the floor caused this customer to have any worries, okay? So now they're going to the 9-ton furnace. So the customer used 2 bags of no bond material before installing the floor. And again, they use the exact same thing. They're going to use the jolter. And we did use Defender on this form again, just to let you know. So the ideal rammer vibrated the form for 15 minutes in the taper, and 2 minutes every 4 inches, going all the way up the wall. Again, they did their normal center with solid charge. Quite frankly, in a furnace 9-ton, I would, in this particular case, I'm probably going to recommend that we liquid center with heat. So there's several ways of centering a furnace, but liquid center with heat, where you heat it to 1100 degrees, 1000, whatever you can get, with charge in the bottom, and then you pour liquid metal. I think that will probably enhance their hot face. So the hard hot face would have benefited from Defender coating on the steel form, as we found out. So the 9-ton furnace using 3,400 kilowatt at 250 hertz. And again, they're using the magnet on this furnace also. So we discussed, better charging practices, of course. There's no space there for them to put the shaker system, so they have no choice but to go with some sort of a magnet or a bucket charge. I think they're trying to talk them into a bucket charge. It's a little bit more controlled. So after 1 week of operations, 88-ton, liner is looking really good and seems to even look better. than what it did on the 350 or the 3.5 ton furnace. And again, they did this one actually without Defender on the 9 ton because they wanted to do another one and compare with and without in the 9 ton furnace. The operator said that the walls took 2 to 3 days to form. So again, we had the same issues without the Defender. So they had to do an emergency push out after 200 feet due to a bottom run out. We're investigating the possible causes of what happened with that, but we believe that there's more to it. There's something to it, more to it than with the silica. They had some operational issue or they had some block issues also. Is that the boron-free silica has been completely washed away by induction current because of hard hot base. We had, I believe, there was saturation. So we lost 5 inches of the material in the surrounding center section, 10 to 12 inches on this intersection, no material left on that whatsoever. So we think the zone has been under a lot of hydraulic pressure before formation of a hard hot face. So there's a possibility of human error during center cycle, but we also need to look at the impact of the KW and the frequency differential might have been between the 3.5 ton. But we believe that what happened was there was a problem in the installation and the furnace got saturated, and that saturation caused very rapid erosion. So next steps and possible solutions, we'll modify XDX to accelerate the hot face formation. So now we're in the process of making a 4th generation. Customer will install 2 coats of Defender on a steel form every time they do it. And center schedule could be modified to increase final temperature and allow for heat to radiate to the floor and promote a hard hot face. And this is where I was telling you, I believe that if you did a liquid center, I believe that would alleviate all of these problems because you would form a much faster hot face, much cleaner hot face. What happened is when you get molten in the bottom first, of course, you have a small amount of metal with a high amount of power. So that metal is just churning and churning very fast, and that material doesn't form a very quick hot face, and it probably prematurely saturated. And that's, Roger? And that's, can't take the boron any longer. Excuse me. This is the next new silica product that we've developed in the market. Sorry. In that last part of the presentation, there was low dust 1.0 BO. This is not necessarily low dust, but it's very low resveratrol silica. Silica is a carcinogen, and about every 10 years, it seems like the silica market goes through this stage of the government comes in and wants to shut people down using silica. Oh, you have to change from silica. It's dangerous for the employees. And it is. That's true. But unfortunately, economically speaking, there's nothing better than silica and iron. So the governments, of course, who know nothing about what we do, don't think about that. They just think, oh, let's eliminate silica. So, and which would cost every foundry about 10 times more than their lining cost. So we've developed this product called TechSil. It's a silica with 99% lower resveratrol silica, meaning that as you're doing the installation, there's almost no harmful silica being breathed by the workers. So resveratrol crystalline silica. So crystalline silica is a common material found in many natural occurring materials. It's estimated that 2.3 million workers are exposed to crystalline silica on the job. Could be in foundry, it could be shot blasting, it could be processing companies. So there's a lot of different areas. So extremely small particles, typically at least 100 times smaller than ordinary foundry sand on beaches or playgrounds, is generated by high energy operations, meaning crushers. So during crushing of the silica, so you're getting the different grains that you need to make the silica, there's a lot of these very, very, very fine particles that get caught in the process. So new material to combat OSHA standards was implemented in 2018. And again, the government was pushing manufacturers of silica to try to find some way to make this safer for the workers. So the goal, we needed to create a new silica product that substantially reduced the resveratrol silica on dry vibratables. Testing was done, okay, amorphous silica incorporated by dry vibratable versus conventional silica and dry vibes. So again, here it is. You can see that all these workers are hooked with monitors so that we can track exactly how much exposure they have to that particular grain size. So this is a 30-ton coreless where we're putting it. So as you can see, here's the results of those testing. If you look at our standard mineral is usually 7.8 percentage weight that, with 10 microns and lower, that's being observed. Texo was 0.03, and our competitor silica was 9.02. So really, there was very little to any respiratory silica that the workers were exposed to. It doesn't mean that you can take off your respirator and live the good life, okay? It just means that now you're much safer than what you were before if you follow all the safety procedures. So the conclusion on the Texil is the respirable killers in silica was almost zero. This allows us to provide material to our customers with new OSHA standards. And it's coming. I mean, the time is coming where this isn't going to be a good idea. This is going to be mandatory, at least in the United States and Europe and parts of Asia. There's already parts of Asia where they are close to making this mandatory. I think South Korea is considering. We're looking for repeat orders. We've had very good success with our trials in this. Enforcement of regulation seems to have been a priority for the last 2 years, and I think we made really good progress. Now, let me go back here real quick. The other thing that you need to look at, because silica is bad for your workers, period, okay? If you're not wearing the proper respirators, if you're not taking the proper precautions, we have several workers that we purchased some companies recently, and we have found at least a couple of them that had silicosis. And that was from working on a line with tap hole clays for blast furnaces for 35, 40 years. And it's that continual exposure is very harmful. So using a respirator and using a new product like this can greatly eliminate it. The other thing you have to do is, if you buy new equipment, for goodness sakes, spend the money and get an automatic push-out device. Because the one thing with this product is, as you're installing it, it's harmless. When you remove it, it goes right back up to the high crystalline silica danger levels. So you have to be able to have an automatic removal device so that you can further extend the safety of the process. And it just makes sense. I mean, in the long run, an automatic lining removal system is going to save you money. It's not going to cost you money. It's going to cost you money up front. In the long run, it's going to save you a lot of money. We've been talking about ladles for a very long time. Probably some of you already know that. And my starting line is the same as I get every time, is ladles are an overlooked opportunity by foundries. When you're going in to look and see, geez, where can I save money in my operations? You look at the furnace. How can I save energy in the furnace? What can I do here and there? You look at other assets, but ladles are typically overlooked. And a proper ladle lining can save you more money, probably 10 times more money, than anything you'll ever try to do inside of your furnaces. It's very difficult to do anything in your furnaces to save money. Okay, if you're using a good product and you have good process and you have good procedures, it's actually very consistent. But ladles, it's a whole different animal. And we'll talk about, one area where we find Foundrymen give the least importance, like I said, consume more refractory than corelesses. When you talk about patching materials and you talk about the working linings, they use a lot of material. Tool for energy conservation. Cost savings to customers by selecting proper refractory, and quality metal, less inclusions. All of these things are things that you can focus on. We can work as a business partner, and you have to work as a business. You have to have trust in each other that we're working towards the ultimate goal of providing the best lining. That may not happen on the very first trial. It may not happen on the second, but you're always working towards a better goal. Regardless if we're working together and we're tracking the cost, most important, then we can look at that bottom number, at the end of the campaign, how much patching, how much energy was used, how much regular lining, formers, all of these things, and then we can give you a pretty good idea of operational cost of a lining rather than how much you pay per kg for something you throw into a ladle. I see the worst products in the industry being used in these ladles, the worst, in most places I go. And the same thing I hear every time is like, well, it's cheap. Well, it's not cheap. It may be cheap for the first time you install it, but it costs you money in the long run. So configuration of ladles and product selection. So the configuration ladle with the backup refractory depends upon lining thickness from the OEM. This is a really important thing for any of you who are purchasing new ladles from a ladle manufacturer. Ladle manufacturers give zero thought to refractories. They give zero thought to how much heat you're losing in a lining. I mean, how many ladles do I see here that are 2 to 5 ton and they're using 50 mm of refractory? And then somebody tells me, oh, we're losing too much heat. I'm like, well, you know, there's not much you can do at 50 mm lining to try to save yourself energy. So you need to kind of push, and this comes from the initial design because you have to be able to maintain certain weights at the ladle as well. Those weights have to correspond with cranes, has to correspond with space that you have in front of the furnace. But if you can work with the OEM, the manufacturer of the ladle, and you can work with them from the beginning, and you can get yourself 100 mm or even 125 mm lining, depending on the size of the ladle, then we can start to recommend really good processes that can lower your heat loss. And if we can lower your heat loss in the ladle, we can lower the tap temperature in the coreless. If we lower the tap temperature in the coreless by 50 degrees even, we can greatly enhance the lining life of the silica. So it just keeps building. I mean, if you do things correctly, it reduces cost everywhere. And with high energy costs coming, if you can save energy cost by reducing your temperature, is well worth it. Metal chemistry is also a current issue. Lining thickness plays a major important role. Again, like I said, working with your ladle manufacturer is absolutely critical in a new startup or you can do it in an existing operation. You just got to make sure that you have crane capacity and all of that. So configuration of ladle products. This just gives you an example of one that we, an engineer designed ladle for us. Heat loss around 212 degrees. You can see where we put the different products we put. But anyways, this is an insulating castable for the lid, a precast for this dam portion right here, and then quick cast 62 for the working lining. And then if you have enough space, you can put board, you can put paper, and that way it really reduces your heat loss. But heat loss also is good in a ladle if you have buildup problems, because the less heat you lose, the less buildup. Buildup is a function of heat loss, partly. That's part of it. It's a chemical, but it's also a function of that. So refractory selection, various refractories for ladles and its advantages and disadvantages. So you have bricks, dry-by variable, castable, plastic. This is called Vibraflow, which is a product that we have where it's like a kind of vibration plastic, basically. Precast. So then there's certain additives that you can put in to the refractory to enhance the performance depending on your operation. Your ductile iron, you got silicon carbide to stop the buildup. If you thermocycle the ladle often, you can put fused silica in the castable to help stabilize the thermal shock and reduce cracking. If you have problems with strength of the castables, with buildup, with corrosion and abrasion resistance, chrome oxide is a really good additive that you could use in ladles to help increase the lining life and reduce problems. We are with bricks, advantages and disadvantages. The advantages of bricks is they have good high hot strength. The resistance to acid and alkali attack, good abrasion resistance, and of course fast drying because they're already dried. Disadvantages, slow installation time, lots of joints. I mean, basically you're building a lining with cracking. Skilled workers, it's hard to find skilled workers who are really good at laying brick, and more prone to thermal shock. So if you thermal shock a brick, you're creating hundreds, maybe thousands of cracks because of the mortar joints. Sorry. Castables, very good resistance to chemical attack. When I say castables, I'm just being general because you know there's so many different types of castables, but this is a generality. Monolithic, no joints, one solid lining, very high hot strength depending on what material is being used. You know, conventional castables have worse high strength than low moisture. Low moisture have very high hot strength. Very tight grain structure, so you get a very consistent tight grain structure from the installation. Quicker installation. Forms can be reused over and over, and they can be shave repaired, where bricks cannot. So, and we'll talk about that later, about typical processes that we see here and how we can improve it. Limitations is you need mixers, vibrators, special equipment. You need skilled workers also. You have longer dry out time, and former is required. So those are kind of the advantages for those. Dry vibe, which is also a viable lining material. Not used very much, but it's viable in certain cases. Few equipment needed. You can do it by hand, basically. Okay, you can hand make your tools in the shop. You need skilled workers. Longer dry out time. Oh, sorry, wrong one. Can be installed with inexpensive worker and proper supervision. Better thermal shock resistance, a very long shelf life, and much faster sintering time. The limitations are low resistance to chemical attack. It's very hard to get a really good density in a dry vibe in a ladle application. So you get a lot higher porosity than what you would in a low moisture castable. It's difficult to shave because it's not necessarily the strongest. Lower strength at operating temperatures, takes more time to install, and like I said before, higher porosity than what you typically find in low moisture, low cement castables. Probably the fastest growing area for ladles in the United States at least, and in parts of Europe, is precast solutions for the ladles. So, you know, the advantages and disadvantages are many, okay? Consistent and controlled manufacturing, meaning that when we make these, we can control everything. We do very slow heat ups, we do very slow cool downs during the drying process, specific equipment being used. It's very fast, minimized heat up, easier slag and dross removal, lower porosity, extensive product offering. So limitations is really cost, okay? Transportation can be eliminated because you can find ways to pack it, no problem. But cost. But if you can reduce the amount of labor that you have, you can probably reduce the amount of people in that department and switch them someplace where their talents could be used much better. Then these types of shapes have a place in some foundries. Caterpillar is one of our biggest customers, and we supply them precast ladles all the way up to 15-ton capacity. And every single ladle they have from 15 tons down to 2 ton uses a precast shape. So configurations of ladles. There's various products and various product ranges that can be used, okay? Quick cast 62. And with that, we typically add, with all of these, we typically add stainless steel needles, okay? Stainless steel needles give you better thermal shock resistance, but it also, more importantly, helps that castable maintain its strength over cycles. You know, if you look at any product bulletin from Allied or any competitor, you'll see permanent linear change, and then you'll see strength. That's all based on one thermal cycle. But if you thermal cycle a castable again and again and again and again, the strengths just go like this, to where you're almost to a point where it's almost zero strength left. And that's what causes these to wear away. So if you add, and what we found was 6%, 3% does very little. It helps with thermal shock cracking. If you want to retain strength, 6% is required. So Duracon 7030, and 62 is a molite based, by the way. So you're talking around a 65 to 70% alumina type product. And then there's lower alumina, you know, because gray iron, copper, brass. I mean, you really don't need that high alumina content because it's not that aggressive for silica. So it's a fire clay based low cement castable. Again, we talked about Vibram. That's a vibratable plastic. It comes in like baggies, and you pour it like you're pouring drive-by, but it's got moisture. But when you hit it with vibration, that moisture releases very quickly, and it flows like a castable. But you don't have to have a vibrator, a pencil vibrator. You just need a shell vibrator, which could, mold vibrator could use, anything like that. So most foundries have it available. And then, of course, you have plastics. These can be hand rammed. Phosphoric acid plastics are probably the best to use. There are phos-free plastics as well. And then DV, which is 916. It's an aluminosilicate-based, fire clay-based, dry vibratable material for ladles. There's also coatings that can help you. I mean, like I was talking about earlier, sometimes the standard process in India is, okay, we're going to use this product, and we're going to use that exact same product, and we're going to put a coating every time we cool the lining down with the same product. Well, castables aren't designed to be cast and troweled. They're designed to be cast. At casting water rates, you get your maximum density, your less porosity, your higher strength. So in order to trowel it, you typically have to add slightly more water, or you have to do the next thing, is you sift out the large grains. And then you start to put it on so it's finer. So what you've done there is you've taken away the large grains. Now you've increased the percentage of calcium aluminate cement. As temperatures go up, calcium aluminate cement strength goes down. So you just did the opposite of what should be done, the opposite. So the coatings are anywhere from a magnesia-based to a graphite-based to an aluminosilicate coating, or even a silica coating, depending on the severity of the operation. So these are just pictures of some coatings that we put on. This is called T-coat. Many of you use it here. Many of you have heard about it before. So why coatings? Coatings act as a partition between the main lining and your cast, or and the metal. We normally call these sacrificial linings. These coatings ease the process for removing slag, and they enhance the lining life. And there's other reasons too. T-coat, for example, is insulating. It's got 3 different types of fibers in it, highly insulating. So if you're using a cover on your ladle, you can reduce the heat loss drastically in your ladle by using a coating of T-coat. It's kind of like cold board technology in a bag, except with cold board you have to go with one thickness. You can't change it. With T-coat, if you are happy at 10 millimeter, you can put 10 millimeter. If you need 20 millimeter, you can put 20. You can do whatever you want. You can put it thicker in different zones than others. So it's very flexible that way. So here's what I was saying earlier, was when you have to add more water, because now you have to trowel a castable that's supposed to be vibrated at, let's say, 8 to 10% water. Now you need to trowel it, so you're going to add probably more like 10 to 12% water. And what happens is strengths of castables are heavily affected. When they say water range between here and here, that's a very serious point that you need to look at, because we know from testing that if you stray from that, you're not going to get very good hot strength. So here's just an example of water content, 12, 13, 14, all the way up to 18. And this is your modulus of rupture. So at your maximum, or your recommended, optimal water temperature, this one is when you mix it a little bit lower, depending on what kind of equipment you have, then your strengths are pretty good. The minute you start increasing that water content, drastically reduces the strength, drastically. And this doesn't even take into account, like I just said, if you're sifting the coarse grains out, now you have a fine material, and you're like, oh, this trowel's really good. Well, yeah, it's all cement. It's no longer really the chemistry of the product that you think you're buying. It's all cement. So, and a controlled heat up. There's so many things that's important with that, okay? All moisture added in the castable can be removed before putting the ladle into operation. So moisture remains both chemical and free, meaning free water driven out around 100 degrees, like boiling the water. And then you have chemical water that's driven out at different stages throughout that process. So you have to think of it three-dimensional as well, because it's, you know, just because you got, let's say you're heating it at 260, and let's say you have 4 inches of ladle lining with some, you know, paper on the shell, you're not getting 260 all the way through. So a slow heat up is required so that you drive the temperature as far back as you can and maintain a more even temperature. So that slow heat up is required. So you can see at 100 degrees C, 60% of the water is gone, okay? Now comes the chemical water. 15% gets removed at 230, 17 gets removed at 260, and 8% gets removed at 550. So to remove the moisture from the system, you need to follow very strict rules. No wood. Wood firing is not an approved source of drying a ladle. You'll never get the water out at the temperatures of wood. You'll never get it out. And if you do get it out, you'll crack your lining because you have no control over the schedule and the heat up. Sometimes it's done in an emergency. Some people do it and they say they have success. But we're not talking about, oh, we're happy with what we're doing. We're talking about how can we do better. And I guarantee you, switching from wood to a more controlled system, you'll do better. Gas is recommended. However, there are some good, very good resistance, you know, heater type applications with automated controls that also work really good. So let's talk about some case studies. And like I was saying, most of these products that we just talked about are not going to be the cheapest cost per kg. They're not, because it's not the same thing that's being used in most instances. Much higher technology, much better design, lower moisture type castables, you know, designed for a specific temperature range. So they're talking here about, with these case studies, is basically daily cost for patching of a ladle. So 2 ladle per day are required, okay? So they're looking at the cost by using the right product or using the wrong product. The wrong product is what makes your repair cost much higher. So here we have a fire clay based patching, 50 kgs per patching per ladle, 100 kg in a day. So there's 2 ladles per day, so 100 kgs a day. Doesn't sound like a big deal, and everybody, oh no, it's okay. Well, over time that adds up, okay? It adds up. Not only in money, it adds up. If you're eroding these things fast, it's going into your metal. Some of it's being slagged off, some of it's going into solution, and you're going to have issues with quality. So it's an 80% aluminum castable, and they 30 kgs per patching ladle, 60 kg per day. Here's the cost of the diesel to dry it. You can see they have all of the figures. 90% aluminum coating, where they're using about 22 kgs patching ladle, 4 kg in a 2-day. The cost of that. Labor cost, $300 per ladle. So then you look at the cost of the allied, and they have to have all of these products because it's more labor intensive and there's more things they have to repair. So here we're talking about T-coat, what I talked to you about, the MGO insulating type of material. And they're using about 15 kg of material in 2 ladles at 92 rupees per kg. Diesel, patching of product 7055, which is a fire clay based moldable type plastic material that has good trowel. You could actually trowel that one or hand install it. 200 kg per month, 8 kg per day. Considering 25 working days, 83 rupees per kg. So labor cost, 300. So even though these products, if you saw the price per kg, they're probably at least almost double what these are. But by following and tracking less patching, less downtime, less labor, less fuel, it's actually half the cost, more than half the cost of what they consider a cheap material, okay? That material no longer became cheap, that material became expensive. So in summary, challenges in traditional practice is refractory consumption is more. Not only that, the other problem, when you start to modify, meaning let's say you trowel a castable that's not supposed to be troweled, you have very high porosity. If you have high porosity, you're going to have a lot of buildup, a lot. So that porosity is space between the grains on the hot phase. And when you get a fluid slag, that stuff just saturates like a sponge into your lining. So 2 times preheating required, so more diesel fuel was required by this customer. Rinsing the furnace with metal if the ladle sits idle for too long. Because your heat loss is so high, sometimes you have to do a wash heat on your ladle to get the temperatures back up again. And because you have to repair it more often. You have to repair it more often, you lose the temperature, you got to bring it back up to temperature. And manpower cost was tripled. So what did we achieve here? Ladles running for 3 shifts. Only 1 ladle needed for 3-shift operation. Only 15 kgs consumed for the coating. Diesel was reduced, heat loss was reduced, and manpower was reduced. So everything we wanted to accomplish, we were able to accomplish. Here's just some pictures of the cost savings in a lip bore ladle. And you can see the condition of the lining after 24 hours of operation. Looks really, really good. And again, here's another case study. It's basically the same thing, but different customer, different size ladle, different procedure, different process. But fire clay based, again, they're showing the cost of what the lining is. $2,700. It's a patching mass. And again, you can look at Allied's. Much higher. But coating material, they use about 5 kgs. This one they use about 180 kgs per day. We're using about 10. 10 compared to 180 makes that price very low. Diesel, much cheaper. Labor cost, again, much cheaper. So again, this is 3-month running cost, considering 26 working days. And you can see that in the end, the difference in cost is huge. Even though these cost more per kg, at the end of the day, it saves 3 times almost, 2 times at least the value. So it's operational cost versus kg cost. So again, summary is the same thing, okay? Slag buildup nearly a treatment section. Daily 3-time ladle needed to be changed. In an hour 6 treatments of 144 and 24 hours. 2 times preheated. Rinsing without metal, or with metal, sorry. Ideal for 30 minutes to 1 hour. Manpower cost was higher. So ladle running for 18 hours, okay? With the use of flux also. 10 kg consumption of T-coat, okay, much lower. Diesel consumption reduced, manpower reduced. Due to continuous operation, the metal impact localized area is happening after 20-25 days, so we're working on suggesting tundish cover over the treatment ladle to increase the lining life. So that's basically reducing, gives you a more focused area to pour into, but it also insulates your ladle and reduces splash. So there's certain things we're looking at in order to, again, take it to the next level, okay? You're never satisfied. You should never be satisfied. You should always be looking for something better. Again, here's case study 3. Customer with the old configuration with 50 mm Super Duty bricks and a 30 to 40 mm conventional castable. But again, most likely, they're sifting this so they can get a finer grain so they can install it better. And if they're not, they're increasing water content, which is really affecting their lining life. So here they have 75 mm quick cast 62, and they're showing also one with where they put paper. So furnace metal temperature, after treatment temperatures, first box, middle box, last box. So average temperature drop from box number 1 was 6 degrees. Traveling time from number 1 box to the last box is 5 minutes. This is a foundry and color pour. So heat loss from first box to last box was near about 30 degrees. So in summary, this helps them to reduce the temperature of the melting in the cornice. Again, like I said, since we used the coatings, we used the proper refractory, we used the proper backup, and we had a cover, we were able to reduce the heat loss by 30 degrees. That's significant. If you can come out of that cornice 30 degrees lower, that is tens of thousands of dollars a year in energy, depending on the size of the furnace. So also there were some cases where the temperature dropped were high, and the customer was not able to pour the last box. So they also had losses because they weren't able to pour as many castings because the metal temperature got too cold for their standards. Everything okay? We go, okay. So again, cost savings, study 4. 2.5 ton transfer ladle. Product used is a precast ladle with a dry backup. So the application is ladle used for transferring 2.5 tons of metal from a 15 metric ton coreless furnace to a holding furnace. Installation, bottom lined with dry ramming mass. First you put in the dry, level it, set it, fill it again with dry, and then cap it off typically with a wet ram or a plastic. So results, the first installation at this particular plant in July 2022 performed great. Full campaign for cast ladles were only 6 months, and with shapes we were able to surpass that goal. I believe it went all the way up to 9 months. So they got an extra 3 months of operation from the precast shapes, and it's mostly because of drying mistakes and installation mistakes. The second ladle was installed in October 2022, and additional orders are coming in today. So these precast ladles are not only outperforming their regular castable, but it's really decreasing the amount of labor, energy from gas, all of this. So it's cheaper in some cases it's cheaper to run in the long run, again. But that's a case by case, because precast shapes do have some limitations in that they're very expensive. So the next thing we're going to talk about is elephant foot erosion, which everybody seems to struggle with, and some people struggle more, some less. It's usually a procedural issue. Everybody's like, how can we eliminate elephant foot? In a lot of cases, you cannot. You can't eliminate it, okay? It just happens. But what you can do is you can slow down the rate of erosion. You get a lot of stirring action in that taper section and floor, lots of it. You get a lot of mechanical abuse. All of this happens, and there's a lot of chemistry variations that are typically happening. So the best you can hope for in most cases is that you push it to get more lining life, but you're never going to be able to eliminate it completely. So what is elephant erosion? So it's erosion of a coreless furnace. It's erosion of the sidewall and the taper and the floor. It occurs in the active coil, typically the lower portions of the furnace. It's more predominant when melting ductile iron, and several reasons for that we'll go over. It's more likely to occur with lower silicon containing metals. So the development of elephant erosion is based on the field experiences linked to 8 different causes. Installation of the working lining can cause it. That means you get saturation. You get saturation, that actually lowers the melt point of the silica and can lead to rapid erosion. Sintering, again, those two come together. If it's improper sintering, again, you're going to get either penetration and superheating or saturation and melting of the lining. Chemical reactions of the initial charge materials. Okay, charging process is most critical for elephant foot erosion. Okay, if you want to extend the lining life of your coreless, stop putting steel first. The worst thing you can do is put steel on top of silica. Stop putting carbon in the bottom of a furnace. That's another worst thing you can do. So there's other processes that you can do. You can charge in returns. You can charge pig iron first. But steel shouldn't be added until you're about 50% molten. And then that can be added, and it has less effect. And by that time, you're able to add ferroalloys to adjust it very quickly also. But throwing carbon in the bottom of a furnace of a coreless is the worst thing you can do. The worst thing you can do to it. Excessive uncontrolled superheating. I mean, if you're freezing metal in the bottom, and we have people that think that because they freeze the metal, they can heat it. Not here. I've never seen it in India, but I've seen it before in other areas. Sometimes they intentionally would freeze metal in their furnace thinking that, oh, when I start it back up, I can go fast because I have dense charge. Well, what happens is bridging and superheating. If you freeze the furnace, you better heat it up really, really slow. Because every time, if you heat it too fast, you're going to bridge, every time. And then you're going to have an uncontrolled erosion that you'll have no idea is happening until it's too late. altering the thermal gradient of the sidewall and the floor, insufficient water cooling, metal thinning, and the presence of non-ferrous metals inside of the scrap. So issues related to installation. This is one of the least areas for erosion, since most of the foundries are lining their furnaces with pneumatic and electrical vibrators. Rarely. I mean, this one's a very easy way of checking. If you think you have installation issues, we check the density, boom, we know. If you're not, getting the proper density, then we have to change something in the installation process. That's a simple. Still, we recommend to give more attention while thinning the refractory in the taper section. Refractory should be added in a controlled manner of 4 inches per layer. The bigger issue is when you get to the taper. Rather than going 4-inch layers, you should actually go 2. And you need a tool that can get down into the taper section, depending on the angle, how severe the angle is, because it's very difficult to compact that material. Very difficult. If you're using a jolter, then you want to decrease your rate of ascension. So you need to slow down how fast it raises, and maybe half of what you do for the sidewall. Sorry. It can be somewhere between 15, we already talked about that, sorry. So sintering. The purpose of sintering in a coreless induction furnace is to develop optimum ceramic hot face. The intention is to develop a ceramic hot face that has minimal saturation. Sintering refractories requires accurate temperature control. Thermocouples. Every time I go somewhere, how do you sinter your furnace? I go 100 kg and then I stop for 10 minutes. I go another 20. They have this kg site. That means nothing, and that changes over time. So if you're going to use a kg per minute type of sinter cycle, then periodically, like every 6 months, you need to drop some thermocouple wires to make sure you're still following what's approved. Careful selection of charged material, starter blocks, used for initial heat up. If any one of these aspects is ignored, the area in the furnace that will first suffer is going to be your taper and your floor. Chemical reactions. Thermodynamically, there's an equilibrium carbon ratio. So if you throw off that carbon-silicon ratio, and your metal needs silicon, for example. So you're charging steel in the bottom of your furnace because you claim that it melts faster and you can save time. Well, that may be true. I don't believe it, because there's other ways that we can, by controlling the scrap size and using different types. If it's hungry for silica, silica is a very unstable material. It wants to give up its oxygen really simple. So if you're dumping carbon in the bottom of the furnace, or if you're putting something in there that has, very low carbon, and that carbon-silicon ratio is way out of range, then that metal is going to take the silicon to try to make it more even. And it's going to take it from the silica. The sequencing of charging materials can play a key role, and it does play a key role. I mean, I've heard several excuses why they can't charge, returns first, why they can't charge pig iron first, why steel has to go first, why you have to put carbon in the bottom. No, steel does not go first, no, carbon does not go first. It does not, period. And there's so many ways for you to increase lining life. That's the biggest, your charge sequence. You can play with it, you can adjust the percentages, whatever you want to do. I had people I went to a foundry in Turkey, had a 30-ton furnace. They were putting 30% borings on the center cycle in the bottom, and wondering why they were washing out the taper section and floor so quickly. They had no idea what the chemistry was, first of all. It was wet, second of all, and it's quite aggressive with the oils. So anyways, charge sequence is important. Even if you have returns, they say, oh, we can't charge our returns because we don't sandblast them. They're sand. Sand is silica. Additional silica in the bottom of that furnace isn't going to hurt you. You could add ferrosilicon in the bottom, and that would probably help you. So if you have sand on your returns, even if you get buildup in the taper section, I can get rid of buildup in the taper section in 2 hours. That's no problem. But if you erode it, you can't add refractory back. So this is just telling you, to avoid. This is the carbon, silicon equilibrium, which we've seen many times, kind of where temperature lies and what happens with all your, the aggressiveness. So if you have a low carbon, low silicon, you're going to have issues. if that's what you're melting in steel. If you're putting pig iron and you have high carbon, low silicon, which is typical, then you need to put some ferrosilicon in the bottom of that furnace because you need to stabilize that metal as quick as possible. Otherwise, it will take it from the lining. Very easily take it from the lining. And that's all silica, okay? No matter whose silica you use, that is an international fact. Chemical reactions of the initial charge, as you can see here, here's what we're talking about. Inductile-based iron, you're right around 3.4 to 3.9, 0.7 to 1.8. Treated ductile, 3.4 to 2.4. And here's pig iron, 3.5 to 2 to 0.8. Carbon steel, 0.1, 0.5. Silica, 0.2. When you start getting down into these, you have big issues because it does take the silica, and it's going to take the silica from the bottom first because the bottom's going to be higher temperature. It's going to be more skewed chemistry, and it's going to come out quickly. So, oops. Also, design of the taper. This is, everybody says, okay, this came from the OEM. And yes, that comes from the OEM. But you can play with taper design. And you're not going to really affect the safety of the furnace, okay? We can't tell you, oh, hey, change it to this and you're going to get 20% more lining life. We can't tell you that. But you certainly can change your taper and your form, adjust and track the results. And then you can find what's optimal for your furnace. These are standard that comes for decades with these size furnaces. Taper section, the foundry should not expect the refractory to flow down and around. This is what I was talking about earlier. I would reduce the thickness of the layers when you get into the taper section depending on the severity of the taper because you really have to try to get in there. And if you're using a jolter, then you want to slow the rate of ascension so that you're getting more vibration in the taper than you do in the sidewalls. All of that is normal so that you can get maximum density. If there's any question whether you're getting maximum density, when you take out your lining, you set a piece aside from the taper and you send it to us and we'll check the density and we'll tell you exactly how well you did. And you can do that on a periodic basis. We're more than happy to do that. That's part of our service so that we can keep control of your process. And we all lose control of processes, even in the refractories industry. We do sometimes too. So it's nice to have those quality checks working together as a team. Excessive uncontrolled superheating, we talked about that also. Freezing the furnace. Adding too fine a charge in the bottom of the furnace, too dirty charge in the bottom of the furnace, where you're going to get superheating. And superheating is simply using too much power, or bridging, where you're using the normal power, but you're heating a much smaller volume of metal. So altering the thermal gradient, changing the thermal conditions of the taper section. And again, we already talked about this also. Change in thermal conductivity of the backup, meaning using mica or paper. Change in the slip plane, a change in the taper design, anti-interruption in the cooling water. So, if you power outages and you don't have a generator backup and you lose coolant, it only takes a few seconds. You can lose your water circulation and you're done. That lining is going to start to center very quickly, and you have very, very little time to bring it back up and stop and build up on the surface of the refractory. So sometimes getting metal behind the buildup is what they're talking about. Sometimes in the taper section, if you get too much buildup, it infiltrates between the lining and the buildup, and that becomes a superheating condition as well. Metal finning. Metal finning and coreless, of course, we know it comes from thermal shock, but it also comes from saturation. So if you have a saturated lining, it's much less resistant to thermal shock than if you have one that's centered properly. So if you have a shallow hot face and you thermal cycle it, cracking will be less. If you have saturation from improper centering or finning, can happen because it's going to crack worse. And those cracks from saturation, in some cases, won't seal on their own. So that makes it even more difficult. So anyways, finning is an issue, and finning can cause, the reason in the bottom is that that's typically where you get molten first. So if you don't use a proper daily heat up cycle, and we call cold start procedure, then a lot of that's going to take place in that taper section and floor. And that's going to cause, once you get a fin, now you're putting tremendous amounts of energy into a very small section of metal. And it superheats all the way up into 3,500, 4,000 degrees quickly. It causes an issue. Again, the presence of non-ferrous metals. So in conclusion, strict adherence to installation, use quality charge material and preferred sequence and sizing. Zircon addition to the silica refractory. It's been proven that elephant's foot erosion can be reduced when zircon is added to silica. Zircon is a non-wetting agent. Greatly reduces wetting of the metal to the silica refractory. I would say that it's a 50-50. Sometimes there's a benefit to zircon, people see it right away. Sometimes they don't see anything. The problem with zircon, it increases your cost. Zircon is becoming very scarce, very hard to get. The harder it is to get, the higher the price. So, taper, the design of the coreless melt and form. Utilize shave repair practice. So, all of these things can help you extend the lining life. Changing, playing with your taper and doing a proper shave repair. And that's it. So, do we have any questions, or now you can open it up? Well, like I said, we prefer that you put a minimum 100. Well, it depends. If it's a 2-ton, 100 millimeters is what we prefer. But really, the thicker you can make, usually we prefer between 100 and 125, okay? If you're below 2-ton, like a 1-ton, 500 kg, then we prefer 75 to 100, so in that range. The bigger the ladle, the more lining thickness we'd like to see, okay? Just like a coreless, you see a 1-ton coreless, you're gonna have a 3-inch lining. You see a 10-ton coreless, you're gonna have an 8-inch. Same thing. But if you can make it thicker, it depends on what you're trying to achieve. If you want to increase your or decrease, your heat loss, then allow us enough space that we can put microporous board, backup brick, and castable, and a coating. And then we can really control heat loss. If you're looking to extend the lining life, because you get, you're using 50 mm right now and your erosion rate is so fast, then we need thicker for that. If not, we'll be around, you can have dinner, and as you're eating dinner, I'd be more than happy to stick around and talk. But if that's all, I really appreciate it. It's a great crowd. I'm really came out. Oh, got a question?
During sintering process, we are using the pig iron charging, sintering process. While using that pig iron, if you are having high manganese in that pig iron, it will affect the bottom lining of the furnace?
Extremely. You're using silica, correct? Yeah, the high manganese, it's going to kill it. You're talking about an extremely basic material. We're attacking an extremely acidic. And manganese is about as aggressive as you can get. So you need to avoid as much of that in your charge as possible, especially in the bottom. Okay?
Further questions, or we can ask, like Chuck said, we can discuss over dinner. So.
Okay.
Yep.
Thank you.
Thanks so much. Gentlemen, I'm sure you all had an interesting learning session today from our seminar on the topic latest refractory solutions for cost-effective productivity. So we'd like to thank our speaker for the day, Mr. Charles Essman, Business Manager International Allied Metal Products USA, for taking time off his busy schedule and being with us today and making us rich with knowledge. Further, we'd like to thank all the members who joined us today. Thank you so much for joining us on time. Thanks a lot for acknowledging our invitations by WhatsApp or by mail and joining us all the way from, we have a lot of customers. We have people from Sholingar, Naidupet, Ennore, Gumdipundi, Sriperumbudur, Thervaikandigai, and various parts of Chennai. So thanks a lot for that, and we are really thankful for the same. I'm sure you had a wonderful learning experience. We from the Chennai chapter will be conducting very such interesting programs, both physically as well as through webinars. So we'll be sharing the information with you soon. So thank you so much for joining us. And also, like the chairman said, we have a very active IIF Chennai chapter YouTube channel where we have more than, I would say, 32 to 33 videos that are already uploaded. This is all technical as well as management programs where we have a collaboration with MMA. So we have, these are very much learning experience for customers who would want to develop themselves more in technological way as well as in the management side. So, so requesting you to please subscribe to our channel. You can just go onto YouTube and just type IIF Chennai chapter. You will be able to subscribe to our channel. So with that, we'd like to thank you all for the opportunity. So thanks so much. Requesting our chairman to felicitate our speaker for the evening, we request Mr. V.P. Prem Kumar, Director, Marketing and Quality, Nelcas Limited, to felicitate him with a traditional Angavastram and a memento. Thanks so much, gentlemen. So I'd like to request our chairman to take over one more proceeding. This is regarding honoring one of our long-term employees with us.
So we might have known Mr. Viswanathan. He was our manager and running IIF Chennai chapter office. After COVID-19, we have no people. He was our long-time colleague with Ennur, and we brought him. He was running the show for the past 2 years, right? Past 2 years. And of course, very good, dedicated and sincere personality. And because of his preoccupation in his hometown, he is living with us. So as a mark of his hard work and sincerity, we have to honor him. Viswanathan, please come forward. Prem sir. So wishing you all the best, Viswanathan. Thanks for being with us for a period, right? Thank you very much.
So with that, gentlemen, we are coming to the end of the day. So we request you all to please join us for the cocktails, which will be served right behind you, and post which you can join us for dinner as well, which is being served just adjacent to the stage from here. So thanks so much, gentlemen. Thank you so much for joining us. Please enjoy your rest of the evening. Thank you.